Good morning, everybody. My name is Kevin Renaud. Thanks for joining us. I'm with Peerless out of Buffalo. This is our 9th consecutive week of our e-learning initiative. This week we have Paul Long once again joining us from Hosemaster, and the topic is expansion joint design, the do's and the don'ts. We're going to go ahead and get started. We do have a very good audience with us today. Again, the geography includes a bunch of states all over the eastern portion of the US. Thanks for joining us. There's a very diverse group of customers with us today as well. Once again, Peerless, we've been around for over 100 years, and certainly we're proud of that, but we're more proud of the role we play in helping our customers work on highly complex projects, delivering on time, and keeping plants running smoothly and efficiently. We do have 3 main sections of our company. The first is Procore, where we focus on the OEM customers, packagers, skid builders, engineering. We also have our process division, and there we are focusing on chemical, pharmaceutical, food, beverage, manufacturing, and certainly universities and government. And finally, our high temp fabrication division. This is one of our newer segments where we work with high temp insulation, refractory, scientific surfaces, and laboratory equipment. So we once again do have Paul Long here. He was with us a bunch of weeks back when we talked about the differences between expansion joints and metal hose, when to use one over the other. He's back with us. Dan Morgan is our continuous improvement manager out of Peerless. He'll be moderating. Greg Barrell is the business development manager for our process division. And of course, me, Kevin Renaud, I'm with in business development. So again, I do like to talk just a little bit about the presenter, and Paul Long does have an interesting history. Many of you may have heard it, but we do have a bunch of people who weren't with us last time. So Paul Long was a starting center with the Ohio State Buckeyes back in '91 and '92. And with that, you have a very, very close relationship with your starting quarterback, who was Kirk Herbstreit. Many of you may know him from College Game Day these days. So it started getting me thinking about the team and looking at the roster. And certainly he played with a bunch of great players, some Hall of Famers, as a matter of fact. And I noticed they all have football cards as well as Paul Long. So when I went to a website to see how much they were, I found prices for all these guys, but nothing for Paul Long. And when I clicked on the price, I found that it was sold out. So in my book, I think you'd agree that, and Paul would have to agree, that that would make that one priceless. So good for you, Paul, way to go. And with that, I am going to turn it over to Dan Morgan, who is going to cover some housekeeping.
Yep. Thanks, Kevin. Yeah, so, a few of you have been with us before, so you sort of know the drill here, but if any of you are joining us for the first time here, I just kind of want to run through how things are going to happen. So in your control panel, you'll see a pane for questions. So as Paul is going through his presentation, this really makes the most sense if we're covering things and answering questions that make the most sense for your application. So if at any point during Paul's presentation, something comes up that you'd like to get an answer for, please submit a question through that questions panel. And what I'll be doing is watching those questions come in and finding appropriate moments to interject into Paul's presentation to make sure we get those questions answered for you. So we're also going to do a little bit at the end too, if we can't get to everything throughout the presentation. So yeah, definitely don't hesitate to ask anything. And with that, I will now turn it over to Paul.
Thank you, Dan and Kevin. I am going to change it over to my screen, or is it showing my, oh, here we go. All right. Good morning, everyone, and thank you for the intro, Dan and Kevin. I found out after the last one of these we did, where you kind of went through the cards, the playing cards, that my wife and daughter bought all 12 of them, and they're in my basement right now. So that is why it is sold out. So there's the answer to that question.
Yeah, but just there you go. Perfect.
Yeah. So I'm going to bring up my presentation here. And as we go through it, I'm going to toggle out a few times just to kind of go over a few items visually, I think, with some samples next to me. can do a little bit more justice than the PowerPoint presentation alone would do. So with that, just wanted to start out, who is Hostmaster? Well, we're a manufacturing company that provides solutions through engineering. So we devote 10% of our workforce at Hostmaster to the engineering of our products and product design and how they adapt and work out into the field. We manufacture 3 nickel alloy flexible components for the industrial world and pharmaceutical world. First is corrugated hose, where we make that from 1/4-inch diameter on up to 12 inches ID. Strip wound hose for bulk conveying or exhaust high temperature applications. We make that from an 1/8 inch to a 16 inches in diameter. And then what we're going to focus on today, expansion joints. And our size range goes from 2-inch on up to 120 inches in diameter. And with that, there's a whole host of different designs and configurations that fall within those parameters. So not only do we fabricate and manufacture the hose and expansion joints, we also fabricate those into completed parts. So we have 90 ASME Section 9 plus certified welders at Hostmaster. That is a photo of what we call Main Street, where at any given day, we're putting out 2,400 completed assemblies, and depending upon the complexity of the expansion joints, we're also putting them out the door from start to finish. We keep a large inventory of components on hand for quick turnaround and emergency rush deliveries. We can do both expansion joints and metal hose in a 24/7 emergency service option. So if a plant happens to be down and the component that's causing that plant to be down is a metal hose or an expansion joint, obviously we understand what that means to the customer or the end user. So we turn it around in quick fashion, can get that out the door from start to finish, from design, manufacture, and shipping. Some certifications to keep in mind as we talk about expansion joints. Hostmaster has several. You can find these on our website. However, some of the ones that pertain to the expansion joint world would be in the ASME world, the ASME Section 8 world, where we have piping off of boilers if we're making an alteration or a repair to a bellows. We also have CRNs for the Canadian market, and we also follow PED and NAHEAD guidelines. We have 4 locations. In Cleveland, Ohio is our main manufacturing facility. It's right around 250,000 square feet. We also have satellites that fabricate our bulk goods in Atlanta, Georgia, Reno, Nevada, and Houston, Texas. So expansion joints. So what does an expansion joint do, and why would you need one in your piping system? It absorbs thermal movements. So if we're dealing with temperature ranges from cryogenic on up to 1200 degrees, it absorbs mechanical movements. So if we have movements acting on piping systems or other pieces of equipment that are going to cause undue stress, we can use an expansion joint to reduce those forces. Leads into number 3, where we're reducing forces acting on installed equipment into a piping system. It isolates and reduces vibration and noise, compensates for misalignment. Some of these components that we manufacture are coupling with turbines and other pieces of equipment, compressors and such, that can be very, very large. And so if we have to deal or make up for a little bit of offset, angular movement, or compression or extension, we can do that in a very small area with an expansion joint. It'll absorb seismic disturbances, facilitates assembly of heavy equipment, and then contains the flow of whatever that media is, liquid or gas. There's several types of devices that can be used to achieve making up for some of those items. If you have enough room, you can put a pipe loop in where it's just a dog leg with piping that's large enough and long enough to accommodate whatever movement needs to be made up in that run. You can use a slip type joint, but with that type of product, there's a maintenance factor that you're always having to address, whether that's monthly or quarterly. And then finally, you have an expansion joint where if it's designed right, we can put that into the system and it'll work and last for an indefinite period of time, depending upon the number of cycles it's going to see in the media and those types of things. EJMA is an association. It's the Expansion Joint Manufacturers Association. They come out with editions, and in those editions, there's calculations on how to make the bellows, how many bellows are needed for certain criteria, certain movements. We abide by, excuse me, the latest edition of EJMA. So what movements can an expansion joint make up for? So it can move axial. So if we're dealing with compression and extension, if we're dealing with an angular movement, and it can also make up for a lateral offset in the piping system. The one thing we would like to try to know about a piping system has to do with pressure thrust. And pressure thrust is something that comes up when that pressure in the system, or when the piping system is pressurized and the joint is pressurized. We try to get all the information up front as to if that piping system is anchored or guided properly. Because if it is not, we need to make sure that we're putting something on that expansion joint to restrain that pressure thrust so that expansion joint doesn't start to grow and potentially damage the piping system that it's been installed in. And here's just a little photo of that. So the more information we can get up front, the better we can design that joint, the longer it will last in the system. Now at Hosemaster, we have, like I said before, 10% of our workforce devoted to engineers on staff trying to make the best component for the application. However, our engineers are not piping engineers. So we're really good at what we make and manufacture at Hosemaster. However, there's a portion of this design work where we're dependent on the end user to give us as much information possible so we can really lock in the parameters of that design. Spring rate is the flexibility and the amount of cycles an expansion joint will make in its lifetime. And I'm going to try to pull up my camera and if it's on, so I think we're working here. Dan, is it working?
Yep, absolutely, I can see it.
Wonderful. So we have a little example of what I'm talking about when we're talking about spring rate. In order to increase the spring rate in an expansion joint can be made from multiple plies. So what we do is we take multiple sheets, we roll those sheets into a tube, we nest those tubes inside of one another, and that allows for a more flexible joint. In this case, here's just a sheet of 1 ply of 030, and when you try to flex it, it's not very flexible. So if an application needs a higher cycle life for an expansion joint, we might be able to go to 2 plies of 015, which equals the 030, and now we get more flexibility from that joint. And then so on and so forth. And then the third ply, 3 plies of 010, we have a joint that becomes very, very pliable, can do very, very high cycles if that application is needed.
Oh, there you go.
So in this case, with the 1 ply, the 2 ply, and the 3 ply, at the bottom, you can see the cycle life goes from 542 with 1 ply. And just by increasing it up to 3 plies, now we can get up to almost 87,000 cycles. So we're up to, I believe, 14 plies right now with our expansion joints. We've made several expansion joints with a cycle life of 100 million cycles, which is considered infinity. But for some people's applications, that may only last 2.5 years. So it's all dependent on what you need that expansion joint to specifically do for your application. So just some specifications, like I said earlier, we go from the size range of 2-inch on up to 10 feet in diameter, a whole host of nickel alloys. The standards are in the 300 series of stainless, but we can certainly get into the Inconels, the Hastelloys, and even titanium. And from full vacuum up to 3000 PSI, and temperature ranges from -450 on up to 2000 degrees Fahrenheit.
Paul, just real quick, we did have a question come in regarding a couple of slides ago about cycle life. Can you just maybe elaborate a bit more on like what exactly constitutes a cycle, or how you would maybe make that consideration?
Sure. So in our world, a cycle would be if we have an expansion joint and we design that expansion joint to compress 1 inch, and that's the only other parameter that that expansion joint has to make, and we design it to 100 cycles. If the joint goes from neutral to compressing of 1 inch back to neutral, that's considered 1 cycle. Now, if it only goes 1/2 inch, that's not completing that full stroke. So it's not officially a full cycle. So it doesn't take that amount of life off of that joint per se. And these, once again, are derived by our engineering staff and their calculations, and there is safety factors built into this. So in that scenario of 100 cycles, once it hits 100, that joint is not going to fail at 101 cycles.
Got it.
It's to give you a time frame if you're doing a preventive maintenance routine, whether that's yearly, quarterly, bi-yearly, at least it'll give you a gauge as you go through and review those items.
Okay, perfect. Thanks, Paul. I'll let you know if there's any follow-up to that.
Sure. The most common expansion joint is a single type bellows. So it's the bellows component with 2 end fittings. In this case, it's flanges, but it can be virtually, any type of metal fitting on the end. We can put beveled pipe if you're welding it into the system, but typically it's a flanged end connection. We can then take that single bellows, and if we don't know if a system is anchored or guided properly, and we want to protect that system from pressure thrust, what we can do is put hardware on the outside. In this case, it is tie rods. And I'm going to try to use the laser pointer here. And so in this case, it's double nutted so that when it's set, that expansion joint is only going to move within that certain distance that we designed it to move in. It won't move any further out of that, and it'll protect it from damaging not only the piping system, but the part, the expansion joint itself. And then here's just a diagram as to how that tied expansion joint would move with the piping in the system. This is just showing we can also put a nut on either side of that tie rod. We typically tack the outside nut in place so it cannot be removed. We've had some instances where someone have moved that nut off of it in order to install it, or they just didn't know what it was. They ground out the tack around that nut and never replaced it. And that can be a very, very critical thing in the life expectancy of that expansion joint, because now it can move past its design parameters, potentially leading to a premature failure. Here's another instance where it's a single bellows, but the hardware of choice is a hinge and it has a pinpoint. So in this case, this expansion joint is only designed to move in an angular direction. So that's a diagram of that. In order to make larger lateral offsets, what we can do is take two bellows, weld them to a common spool piece. And that's called the universal expansion joint. There's a photo of that. We'll come back to what those yellow bars are on the outside of the joint a little bit from now, but those are shipping bars. We put those on at Hosemaster, so from us to wherever it's being shipped to, it doesn't move on its own in shipping and transit, potentially reducing the cycle life of that part. So there's four basic attributes that we look at when we're designing an expansion joint. Obviously, the flexibility, the cycle life, the pressure rating, the corrosion resistance in the actual part and in around the surrounding environment. So if we have some customers that are next to oceans, we're dealing with salt water, so we got to be cognizant of that fact, because that can lead to a premature failure due to corrosion. We try to get as much information, like I said, up front. It's a better design. That joint's going to last longer. So the obvious ones are size, temperature. We have to select the right alloy for the application. We need to know that the motions or the movements that that part needs to make, what the media is, the pressure at which that media is going through the expansion joint. How are we going to couple it into the piping system? So we need to know what type of end fittings. And dynamics. Is it high vibration? Because, you know, we can't get a pump to work in the right framework. So it's pushing excessive vibration down the line, and we have to make sure and mitigate that before it hits a piece of equipment. Some basic end fittings, just we can produce expansion joints with bands on the end to slide over or slip over pipe or tubing to be welded into place. We can put a beveled piece of pipe or a fixed flange if required. The item that I'm holding up is a single bellows with flanges on each end. And in this case, these flanges are called vanstone flanges. So if you can see, this flange will swivel so that it can connect and mate up to the bolt holes of the piping system. So if we're worried about misalignment in any way, we can put a floating flange on there, and that's going to definitely help and ease installation. So if the media going through the expansion joint is at a high enough velocity, what we can do is put a liner on the inside, make sure that that velocity doesn't act on the bellows itself. If we do have a liner inside of an expansion joint, we put flow arrows on the outside, allowing the installer to put it in and then install it into the right direction of flow, because we never want to install it backwards of that flow. Testing options. We can test every single expansion joint, regardless of being asked, is always going to be tested at Hosemaster before we ship it, but we can also hydrostatically test hoses on request. We can dye penetrant test, HLT or helium mass spectrometer test, X-ray, or radiographic testing, and then any other test a customer may specify. Some different expansion joint designs outside of just those simple ones where we're dealing with a single bellows unit with fittings on the outside. It all is dependent on what our part needs to do for the system that's going into. So we can kind of do that up front with that information gathering and get you into the proper joint for the proper job. With every expansion joint that we quote and produce, we also produce what's called a design pack. And that's basically everything that you want to know about that joint. So the information about the pressure, at what temperature it's going to work at, the number of cycles that that joint is going to make, the movements that we were instructed to design that joint to. And then we include a print showing if it has hardware on there, where the nuts are placed on that hardware, how long that joint is. So all the parameters are up front and stipulated in that design pack, so you know what's going to come into you, so there's no surprises. We also have the ability to also offer CAD 3D designs of our expansion joints upon request. You can work and request those through Peerless. Also on our website, on our brochure, and I can email it if anybody requests it, but we have an inquiry sheet, and it's just the simple way of being able to gather all of the data that we would like to see in order to design the best possible expansion joint. We also can provide a checklist if you're conducting surveys, whether, like I said before and mentioned about preventive maintenance, whether that's a monthly, quarterly, annually type of item for your company, we have a checklist as to what to look for when going through that. So we want to look at fractures and cracks of the bellows themselves. Are the convolutions of that expansion joint, do they still, does the geometry still look like it was when it was brand new, or is it distorted in any way? Leaking at any of the end connections, OD appearance. So is there any residue that we can find on the outside of the part itself? We want to make sure if that expansion joint has hardware, tie rods, hinges, covers, that they're still intact in the right place. Shipping bars, those were those yellow bars that we tack on that expansion joint in our factory. Have they been removed? Want to make sure that those have, or else that part isn't going to do what we designed it to do for you. And then with the drawing that we supply with the design pack, you're able to check if it's doing what it's supposed to do, right? So is it installed properly? Do we have more of an offset than we originally designed it for, or is it within the parameters of that design? Here's a reason why you would use an expansion joint. So we also make metal hose, but metal hose is typically a longer length, 2 feet, 3 feet. And if we have a shorter distance and we need to make up movements within that shorter distances, sometimes expansion joints are your only choice or option for that. So now we're going to get into some of the don'ts of expansion joints, and then we'll kind of come back and touch on what we should have done or what should be done in the future. But typical failures for expansion joints: excessive vibration, corrosion. So if the media is corrosive to the material we made the expansion joint out of, can lead to a premature failure. Squirm. Squirm is typically when the part is overpressurized. It could happen in normal working conditions if the pressure is just pushed up past what we designed the expansion joint for, or it can happen with either quickly opened up valves that release a water hammer type pressure through the system, which the joint isn't able to restrain and handle. Fatigue. The part just has moved past its life expectancy, so it's given up its life and it needs to be removed, or an incorrect installation. So the first one is a vibration-induced fatigue, and it's indicative of a Z-type fracture of the convolutions, and you can kind of see a little bit of maybe the top portion of where the Z would start, but typically it zigzags perpendicular to the convolutions of the part. And in this case, what we can do, as touched on earlier, is that we can take, if this part was made from a 1-ply design, we can increase the amount of plies, which will handle that vibration better. So corrosion failure, corrosive attack of the bellows, and then it results in pitting, and then residue on the exterior of the bellows, or you find leaking product underneath or around that bellows. So on the left, you can see the pinhole starting on the lowest of the convolutions. If that expansion joint is installed in a horizontal application, typically what happens is that the concentration of the media sometimes gathers at the lowest point. So it's at the bottom of those convolutions. And if it can't be more or less flushed out and it sits there to concentrate, it can turn corrosive after enough time and then start leading to a premature failure. And what we can do there, in order to fix that, we can look at what that media is. We have corrosion charts at Hostmaster where we might be able to select a higher alloy grade in order, so we can move from a 300 series to maybe a Hastelloy or Inconel alloy and mitigate that failure due to corrosion. Column squirm, so there's two types of squirm. One's column squirm, the other one is in-plane squirm. They both happen primarily because of overpressurization of the system. Column squirm is when the actual expansion joint moves out of being in line with the bellows, and then eventually those convolutions, if given enough time under that high pressure, will actually start flattening out from that sheet or tube we made it from. In-plane squirm, still due to overpressurization, but instead of moving out of being in line of the component itself, the actual convolutions will deflect from one another. And then left in long enough, once again, due to that overpressurization, those convolutions will start to flatten out into the tube that was made from. Pressure thrust, that component earlier in the presentation, we want to make sure that we're building a joint that can handle what your system needs to handle. So if the part is unanchored, or I should say, if the piping is unanchored, we don't know if the guides are have been properly installed. If we go ahead and install an expansion joint without proper hardware to be able to restrain that pressure thrust, what could happen is that now left to its own devices, that expansion joint can start to grow and do some bad things, leading to a premature failure. And in this case, once those convolutions are distorted, it can no longer move the way we designed it to move. Shipping bars. So we tack on those shipping bars after we manufacture the joint, so it doesn't reduce its cycle life from us to wherever it's going. We paint them in yellow and we put stickers on there. Do not remove except upon installation. So they're supposed to come out as soon as that part is installed. In this case, they were left on that joint. No one ever took them off. This joint isn't making up any movement in this system. It's not taking any vibration out of the system. So inevitably there could be a component somewhere in this system somewhere that's taking the brunt of those forces and possibly not working as well as it should, or even maybe failing. When a joint has a liner on the inside, I mentioned before, we put those arrows on the outside so that it can be installed in the direction that the flow is going in. If it is not, on occasion, someone won't pay heed to those arrows, install that expansion joint backwards. And in this case, we have two liners and a universal expansion joint. And unfortunately, they installed it backwards, which then took those liners, pushed them back up through. And unfortunately, there's probably some pieces of metal that came off of that liner that are now in that piping system and where they should not be. So we want to make sure that we're installing that properly. We also want to make sure that when we're bolting, if we are using flanges to install this expansion joint in the piping system, that the bolts are inserted correctly. In this case, and I'm going to try to get the laser pointer to work. So we have a bolt that's touching a convolution on each of these sides. And if there's any movement, we're going to start having a wear point, if not having that convolution actually dented. So it's certainly a premature failure waiting to happen, when all they really had to do is take that bolt and install it the opposite way so that it wouldn't come into contact with those bellows. If an expansion joint does unfortunately happen to fail prematurely in the customer's eyes in the field, what we do at Hosemaster on behalf of Peerless is that we can bring a part back, whether it be a hose or an expansion joint, and do a failure analysis at no charge to them or to their customer, and do an autopsy of that part. Define it, what happened to that part when it was in service, include photos of that failure analysis. And in this case, it's a product analysis because the actual hose in this analysis never failed. The customer wanted us to pull it out of service to see if there was any corrosion taking place. And so that's why on some of these photos, you can see that we're looking at the braid wires to see if there's any residue or corrosion happening in it. We've cut open the hose to make sure that the ID, we're not seeing any pitting corrosion on the inside as well. Another option that's provided by Hosemaster and Peerless is that if the component, the expansion joint, is large enough and it is welded to other components, piping, flanges, that type of thing, that are of significant cost, but those other components are good and it's just the bellows component that is leaking, what we can do is actually bring back that part, salvage the parts that are still good and refurbish them, sandblast them, repaint them, replace the bellows portion that are worn or leaking, and then produce a brand new part from that with new bellows, refurbished piping and fittings at significantly lower of a cost. And then here's a case where this is a vacuum degasser expansion joint for a steel mill, where we brought it back. And in this case, we were actually able to do some re-engineering of the part itself. And when we refurbished it, not only did we replace the bellows portion, refurbish the piping, the fittings, and the cylinders, but now we've rerouted some things, and this part works better than the old part that we brought in originally. And that's the end of the presentation. Thank you very much for your time.
Thanks, Paul. We actually do have a couple more questions here. and I'll also encourage everyone again once more that we will be hanging around for another couple of minutes answering questions. So if there's anything else that you're thinking of or that's on your mind, don't hesitate, send it in. We'll also be able to follow up with you after the webinar if that's easier. But so Paul, the first question here, it goes back to the failure mode of vibration. And you maybe don't need to go back to the slide, but what is the best way for a user to quantify vibration and be able to express that to you in a way that kind of gives you a cue that would make sure that you're considering that vibration and maybe moving to a higher level apply to account for it?
So if we could find out what the amount of vibration in the system, if that can be measured up front with frequency and cycles and get that information up front, we can design that expansion joint to handle whatever vibration it may, however much vibration it may see.
Okay, and probably knowing things like what sort of equipment it's installed near might help you guys as well, right?
Sure, absolutely. But typically, if a part had failed previously, if we could bring back that part and do a failure analysis on it, and then we find out that it was one ply, we just know that in certain applications, like on, say, a pump, for instance, one ply may have been originally shipped out with the pump, and if it lasts past its year life and then kind of gives up its life in that time frame, there are other designs that we can kind of go to that are a little bit more robust and would last longer for the application.
Okay, perfect.
Like an accelerometer, and it doesn't happen too often, but if somebody has an accelerometer that they can kind of connect to the system and measure that vibration, that's an incredible piece of information to get into us before we start designing the joint, for sure.
Right. Okay. So definitely touches back on that information gathering aspect and making sure we get as much details about the application as possible.
Yeah.
Okay. We got one more question here. So we touched on it a little bit when you were talking about liners, but didn't quite cover this aspect of it. What sort of considerations need to be made when you're considering either a vertical or a horizontal installation? So is there a certain design that works to cover both? Are there different designs that you need to use to cover one or the other? Can you just maybe elaborate on that a little bit more?
Sure. So for vertical or horizontal, I don't know if there really is much of a difference as long as we have the parameters up front. If we're working with corrosion, obviously that's going to be something of significance, because if it is in a horizontal run, there is more of a chance for something to get caught in those convolutions and so to speak, just concentrate there. In a vertical run, we don't really have to worry so much about that, with the concentration of the media inside those convolutions. Even though some will still kind of get in there, it's not like it's going to be able to just congregate down in the lowest part of that. If we're dealing with an expansion joint with a liner, and then it's installed in a horizontal, or I should say in a vertical run, we just want to make sure that the liner is either not long enough to go in and protrude from the movement into the piping that it's connected to, but that it's long enough that it protects the bellows that are on the outside of it.
Okay, great. We'll see if there's any follow-up to that one. We did have another question come in. We got a couple more here. What sort of best practices do you have for installation of a tie rod expansion joint into a piping system? So, certain orientation of the tie rods, or what position or sequence of steps that you might need to take to make that installation?
So that's pretty much determined up front However, it's determined by where it needs to be installed in. So sometimes what happens is that we'll be told that there may be other pieces of equipment or piping systems or a gangway that are in and around that could obstruct that expansion joint hardware if in our initial design. So there are other ways that we can kind of change the hardware to still get it to do what it needs to do. However, kind of keep it from getting too large on the outside of it so that it comes into contact with other components. So knowing where it's being installed in and around and how much space we have is great to know up front. Typically, it's not an issue because in a piping system, there's more room than not. But on occasion, it's knowing what's around and what obstructions may be there.
Okay. All right, going back, circling back to that question a second ago about the vertical versus horizontal. Another question came in regarding a vertical installation with a liner if the flow direction is upward. So the question is, can the liner, or is the liner just automatically fitted with a drain of any kind so that fluid won't accumulate?
Sure. What we would do in that application is that we would put a drain hole in the liner itself so that that fluid could run back out into the path of the media. So there is in that case. And
Okay.
we'd also need to know what movements that expansion joint is going to need to be made. Sometimes we can put a packing material if there's solids in with a liquid in that application. We want to make sure that those solids don't fall between the liner and the bellows and get impacted into the corrugations, reducing their movement.
Got it. Makes sense. Is that something that happens as a standard if you knew that the liner exists and the installation is vertical upward? Would that drain be included automatically, or does that need to be requested separately?
It would be automatic, knowing that it was in that vertical installation going up.
Got it. All right, I got a couple more here. Both these questions relate somewhat to compensating for misalignment. So we're really wondering if there's any like guidelines on what sort of misalignments can be compensated for in that arrangement. So are there limits to how much misalignment can be compensated for? Do you have guidelines on that? And the follow-up to that is how does that maybe affect cycle life?
So those are both kind of a little open-ended in the respect that there's so many different designs of expansion joints where maybe there's a limitation by diameter on a single expansion joint. If we go to a universal expansion joint, now we can make up for more lateral offset. In the case of axial movement, we have externally pressurized designs that can handle large amounts of compression and extension in a system. So knowing what the maximum possible movements are would lead us in the direction of a specific joint. And if one isn't enough or able to meet the movements, we might suggest making multiple expansion joints and incorporating multiple ones in a piping system to accommodate those movements.
Okay. Would you, would it make sense that, cycle life would be reduced if maybe, you're making up a larger degree of misalignment, or if you're maybe overextending the limits of that expansion joint?
It could. I mean, if you were using the same design and now you're having to make a larger movement, sure, it's going to reduce the cycle life of that part.
Okay. That is actually all the questions we have right now. So I'm going to turn this over to Kevin real quick. He's got a couple slides to wrap things up. But if there is anything else on your mind, keep the questions coming, and we'll we'll make sure we get a mask before we end this. So Kevin, I should have control. There you go.
Thanks, Dan. You got my screen?
Yep.
All right, thanks, Paul. Appreciate it. In typical fashion, I try to anticipate what you may not have covered, but I see on my last screen you've covered everything that I'm showing, including the forensics analysis capability with some more photos up there. But there is the item you talked about with the specification sheet. We've taken your sheet, Paul, and went ahead and put it into an Excel form so it's easier to input. If anyone would need that or want that, there are the criteria that you need. The more you know, the better off you'll be with the outcome of your expansion joint. So thanks again, Paul. We do, again, appreciate your presence. So next week is a bit of a holiday week. So the Friday is the day that we'll be taking off for the 4th, and we are anticipating some people taking off and finally getting out of the house potentially. So what we're going to do really is just focus on our recordings. Right now we have 9 already on our website of past presentations we put together, and with today's we'll have a total of 10. So and today's did have quite a bit of information, so if you were trying to read some of the paragraphs, it will be there for your viewing enjoyment on our website. And there's the link. You can go to our resources and training page on our website. So that said, the following week, we will have Oliver Vels joining us from the UK to talk about to double block and bleed for instrumentation isolation, some traditional methods and current best practices to keep costs low, people safe, and projects running smoothly and efficiently. So that will be Wednesday, July 8th. So with that said, we hope everybody has a very happy and safe July 4th celebration. And I have a little note down there at the bottom, so I don't forget to mention the poll question. At the conclusion of this, you'll see a pop-up. And we think we're on the right track here because we do have a very high level of attendance, but people go to bad movies every day. So if you don't mind, just take a minute, let us know how we're doing, what you would like to see differently, more of, less of, etc. So it will help us guide our future, our work here. So thanks again, everybody, and have a good week.